Okay, so let's talk about derivatives. Okay, many of the concepts that we have been seeing so far in the course lead to this point. Okay, derivatives are a fundamental concept in calculus because they study how a function changes around the point, or is varying across the point. Okay, so let me give you some idea about this. So suppose we have a function f, right? Something like this, and we want to know. Suppose it's like the speed of a vehicle, position, something like that, and we want to know how this function changes in time, or as a function of us is variable, right? So one way of thinking about this is we have f at x1, right, and then we have f at x2, and we want to say, well, in this difference between x1 and x2, right, this function has changed this much, right? So in this interval x2 minus x1, this function has changed this much, right? So this is f of x2 minus f of x1, right? And we typically represent this like this: delta, this is the Greek letter delta, but the capital one, right? And then delta f with respect to x, the increase in x relative to the increase in the variable, right? So this is f of x2 minus f of x1 divided by x2 minus x1, right? But it's clear, and so that's given by the slope of this line, right? So we have this line. This division is actually the tangent of this angle, right? So this divided by this is the tangent of this, which is the slope of this line, right? But it's clear that if we, instead of choosing x2 and x1, we choose a different point. For instance, let's say x3, right? Between x2 and x1, the slope is going to be different, right? The difference change between one and the other is going to be different, right? So in math, what we want to study is how is this rate of change at this particular point, x1, right? And in order to do that, we want to get closer and closer to it, right? So if we want to get these triangles as we want, get closer and closer to it, so we get like the true tangent of this curve, right? This slope of change at that particular point, okay? And that, in order to do that, we need to use limits, okay? And so that's what the definition here does, right? The derivative of a function f, right? It's that rate of change of that function at a point a, right? And it's given by this f prime, right? Of at a is the limit when x goes to a of this quotient. That's the idea that we have been saying, right? F of x minus f of a divided by x minus a, provided this limit exists. Sometimes it will not exist. Okay, when the limit exists, we say that the function is differentiable at a, right? We could also define the derivative as the limit when h goes to 0 of f of x plus a plus h minus f of a divided by h, right? And in this case, what we have said is introduce the limit x is equal to a plus h, right? And when x goes to h, x goes to a, h has to go to 0. Okay, so this definition is equivalent to the other one, right? And so the idea of this is that this derivative is the tangent, okay, the value of the tangent of the curve, okay, this, well, not the tangent, the slope of this tangent, at this particular point. Okay, so that's a very important geometric way of understanding the derivative. You have any function, the derivative of this function at that point is the slope of the tangent, which is the line that touches the function at that point but doesn't cross it. Okay, and also this is the standard way of writing the derivative in calculus 1 courses, but we also sometimes use Leibniz notation, right? So this is Leibniz notation, which kind of fell out of use in some parts of math, but it's actually pretty intuitive, because the idea that Leibniz had was that we were taking very small increments in x and seeing how these increments in f corresponded, right? So this you get the idea of very small increments both in x and f, right? But the idea is that this is not rigorous enough, because you can't define very small increments, because you can always get some smaller increment, right? Because of the properties of the real numbers. Okay, so let's compute some derivatives. Okay, let's get some examples. We have let's see what's the derivative of x squared. Okay, well, f prime at a, right? This is the limit when h goes to 0 of f at a plus h minus f at a divided by but f of a plus h is a plus h squared, and this is just a squared. So this is the limit when h goes to 0 of a squared plus h squared plus 2ah minus a squared, right? Divided by h. So this and this cancel out, and then we have the limit when h goes to 0 of h plus 2a, or in other words 2a. Okay, now because this is true for every a, right, we can rewrite this like this: the derivative of x squared at x is 2x, as you will probably know. Okay, an exercise for you is to derive the derivative of f of x equals x to the n, where n is a natural number. So derive that this is equal to this. The f prime is n times x to the n minus 1 using Newton's binomial formula. Okay, remember that Newton's binomial formula is let's see, x plus y to the n, right, is equal to the sum from k equals 0 to the n of n over k, and this is the binomial coefficients of x to the k, y to the n minus k. Okay, let me write this